So, okay, next talk will be given by Dr. Henrik Dreyer. He's going to tell us about the robustness of critical U1 spin liquid and emergent symmetries in PEPs. Okay, please.
All right, thank you very much for the kind introduction. I'm just going to move the Zoom bar a bit over so I can see my slides myself. Right, okay, good. Right, okay, so thank you very much. I will talk about PEPs today, and particularly about symmetries in PEPs, and I'm going to take a little bit more of a analytical approach and sort of a fundamental approach. So the title of this talk is Robustness of Critical U1 Spin Liquids. That's the application that we have in mind, or that's the example that I'm going to talk about. And the key of this talk is these emergent symmetries in PEPs. So all that I'm going to talk about is PEPs, square lattice, very simple setup. Just before I move into it, this is joint work with Jiao Chen, Lawrence van der Straat, and Ruben Bereze, and Norbert Schuch. And just shamelessly plug here that at Cambridge Quantum, we are hiring tensor network experts for which you can talk to me after the conference if you're interested. Good. Okay, so let's give it a little bit of motivation. See if yep, that works. Okay, right. So there's two motivations to study PEPs with symmetries. One is analytical and one is numerical. So the analytical motivation to study PEPs with symmetries goes back to the phase classification, right? So in 1D, MPS have been spectacularly successful in classifying phases, SPT phases, basically giving the full characterization. And in higher dimension, this phase classification is still open. And so maybe PEPs can be used as an analytical tool to understand something there. And then there's the second motivation, which is sometimes we use symmetries there was a question in the previous discussion session regarding whether we can fix our PEPs tensors to a certain symmetry and have a better contraction, or more efficient contraction. And then we have to know sort of which manifold we live in and if we introduce some bias by using symmetries in our approximation. Now there's two types of symmetries that I know. So there's the typical physical symmetry. So if we expect our physical wave function to have a symmetry, that is usually encoded in the sort of upper picture where we have a string of symmetry operators moving through the PEPs. So again, this is all square lattice, so 5-legged tensors, and then removing or adding these blobs are representation of some symmetry group. Symmetry operations. And then there's other types of symmetries, including these purely virtual symmetries that I denote in the box down there. And so there, nothing happens on the physical layer, and you only have virtual strings moving around the system. And this might not result in any detectable physical symmetry in your system. So this talk is about these virtual symmetries and what we can say about that. Now, these virtual symmetries have been studied for specific examples. In particular, if this red blob, this symmetry operation is a finite group. So for any finite group, you can do some analytical proofs, and you can show various things. You can show that the PEPs parent Hamiltonian has ground state degeneracies, the PEPs has some correction to the entanglement entropy, and you can even show that with respect to this parent Hamiltonian, the excitations fulfill certain fusion and braiding rules. And so these states are these quantum double model states, of which the easiest example is the toric code. And so these states are very well understood and classified, as you can read in this reference. Now, numerically, 2 points about this particular set of states. So they are, if you are targeting such a state with such a symmetry or a quantum double model phase, then in a PEPs calculation, what you typically should do is you should enforce the symmetry by hand, because you can't rely on, if you just did a corner transfer matrix optimization, contraction and optimization, then you would never find the symmetries accidentally. So these states are, you have to enforce them by hand. And this is due to the second fact, is that these symmetries are not robust. So if you have a PEPs with say a Z2 symmetry, any finite group symmetry, if you break that symmetry on the level of the tensor by any epsilon, then you will sort of get a proliferation of these anyons, and you'll get out of that phase, you'll leave the phase. So these symmetries are not robust. So the basic motivation for this work was to extend this picture to continuous symmetries, starting with the easiest continuous symmetry, which is U1. and basically figure out some intuition. What are the phases that are possible? Are they also topologically ordered, like these finite group symmetries, critical, trivial? What's going on? What's the physics of these PETs, basically? Good. Okay, so then we started with the U1 symmetry, and there's two types of intuitions that you can convince yourself. It's not a very difficult computation to do. There's two theorems that you can prove. So something that we call the virtual Lipschutz-Mattis-Ishikawa theorem, and that is basically essentially the same as the one-dimensional physical, the natural Lipschutz-Mattis-Ishikawa theorem, just on the level of the transfer matrix instead of the level of a spin chain. And you can show that with respect to a suitably chosen parent Hamiltonian, a PEPs with a U1 symmetry, you can make these twists. So there will be at least another low-lying state. So if this PEPs is the ground state of the Hamiltonian, there will be another PEPs, which is the one with the string inserted. Okay, so that means that under general conditions, the PEPs with U1 symmetry, with respect to this parent Hamiltonian, cannot describe any trivially gapped order. And one particular example of order that is compatible with this observation is criticality. So in the case where you have a critical wave function with algebraically decaying correlations, you can create low-lying excitations explicitly by using these virtual photons. So you insert the generator of this U1 symmetry on the virtual level of your PEPs, and you make a momentum superposition, and it turns out you can show that this is a low energy state. And for various examples that we're going to show later on, this is precisely what causes the low-lying excitations. So, okay, good. So the takeaway slide here is that U1 gives you a mechanism, a virtual U1 symmetry gives you a mechanism for gaplessness. Okay, so on the other hand, there's also an analytical, a numerical reason to study these PEPs with U1 virtual symmetry, because they are, for example, used in studying resonating valence bonds. So resonating valence bonds have been put forward a long time ago by Anderson to study spin liquids. And back then, in his original paper, Anderson considered this to be the ground state for the square lattice Heisenberg model. So now we know that that's not true, but back then, Anderson thought that the ground state lives in the singlet subspace, it doesn't break SU2, and then this sort of covering of the square lattice with singlets would be a good ansatz. Right, so, let's see, okay. So this nearest neighbor RVB state, resonating valence bond state, we can write easily as a PEPs, as shown in this paper on the very bottom. And this PEPs has a virtual U1 symmetry, and this virtual U1 symmetry is just given by the fact that if you take any region and you count the number of black singlets coming out of the region minus the white singlets coming out of the region, you always get 0. So that's the U1 symmetry here. And the RVB, the physics of the RVB state is also known. It has two kinds of correlations. It has gapped spin correlations and then critical, what we call Bison correlation. So it is a critical state. And indeed, you can now go back and you can create these virtual photons that I've talked about before. And it turns out those are exactly the low-lying states. Good, okay. So now, this is just one particular state. So the nearest neighbor RVB state, as interesting as it might be, it's not an interesting state to start any sort of numerical endeavor. So let's make our family of states a bit more expressive, and let's add some parameters that we can then optimize over. And then one family of states that has been studied various times in the literature is this long-range family of resonating valence bond states. So now here you have again a d equal 1.3 PEPs with a broken U1 symmetry, in the sense that you start with this blue tensor. So I can't point, but there's a blue tensor, a blue 5 like a tensor on the slide. That is the original nearest neighbor RVB tensor, and then you add this red tensor, which I'm describing in this lower box on the bottom right. And what this red tensor does, it sort of introduces teleportation bonds, which then allow you to have singlets that reach longer, more faraway points. And that way you get next nearest neighbor and so forth singlets. So you allow a little bit more of an expressive ansatz. And that's also what Anderson had in mind back in his first papers. Good. Okay, so there's a little typo on the slide. There should be, of course, this wave function doesn't terminate at order lambda square, but there's all even orders of lambda and then successively longer range singlets. Okay, so in this case we have a broken U1 symmetry, and we already discussed that this U1 symmetry is the mechanism that renders the nearest neighbor RVB state critical. So now what's the physics of this state and how can this be used? Well, one way that this has been applied is as a ansatz state for the J1, J2 model, square lattice J1, J2 model. So now with a sufficient frustration, so this is at the most frustrated point in this found in this study, shown on the slide. They make this ansatz where they don't optimize over all PEPs, but only this particular family of PEPs, or they only optimize over one parameter. And then in this plot shown here on the x-axis is lambda, or basically a constant times lambda. It's just different convention. And on the y-axis, this is symmetry for different system sizes. And you can see here that the lowest energy found in the study is for a finite value of lambda. So in this family of PEPs, there's a optimum for sort of the distance of singlets that you allow. And then they say this is a good approximation for the ground state of the J1, J2 model. Right. So at J2 equals a half J1. Right, and it turns out that this energy is relatively good, not quite as competitive as the current energies, but for a one parameter family of states, this is relatively good energy to obtain. Okay, so but what's the physics of this state? We know the physics of the nearest neighbor RVB. What's the physics of this family of long range RVB states? And to study this, there's been a follow-up paper by the authors. And where they show that this family, the phase diagram of this family is that first there's an extended gapless phase for small lambda, and then up to a lambda critical, point lambda critical, where there's a phase transition into a Z2 spin liquid. So from a U1 spin liquid into a Z2 spin liquid, and then back to a U1 spin liquid. So there seems to be some kind of duality there. Right, okay, so this is surprising in the sense that we know that that U1 gives you, in principle, a mechanism for creating gapless excitations. But on the other hand, we know that in this family, on the level of the tensor, we have broken U1 down to the level of down to Z2 immediately. So for any finite lambda, the virtual symmetry of your PEPs is Z2. It's not U1 anymore. So if the state remains critical for a finite value of lambda, then maybe this U1 symmetry that you've broken on the level of the tensor can come back in the low wavelength limit. It can be emergent. So that would be quite interesting and surprising, because we've just discussed for the finite groups, this can never happen. For these finite quantum double models, you can show that adding any amount of perturbation, they can never be emergent. Yeah. So here maybe something different might happen. So let's go to let's try to understand this a little bit better. And so the way to think about emergent symmetries and relevant and irrelevant perturbation is with a field theory approach. So to understand this field theory approach, let's do a little bit of an interlude. So let's do the dimer model. Okay, so the dimer model came up back when the RVB model was the RVB states were very fashionable, but they have a bit of a complication in studying them, because all of these singlets are not orthogonal. So then when you do sums over singlet configurations, then you have to basically keep all the cross terms, and that makes doing computations, doing these sums makes that very difficult. So then back then, Müssner and Sondi and many other collaborators had a series of papers where they started with the dimer model, where they basically take the singlets and make them all orthogonal, pretend they're all orthogonal. And in that case, you can actually you can prove some things and write down a field theory for that. And then hopefully the RVB physics is sort of within the same phase. And maybe you can say something about that. And indeed, what they found is when you write down the dimer model, it's also, and has an easy PEPs description. then you can write down an action that is compatible with all the symmetries that you expect. And it turns out to be a Coulomb gas, or in this talk, I'll refer to this as a Luttinger liquid. It's just a Wick rotated version of the Coulomb gas. And you can see that this field theory has two terms. So the first term is this grad phi square term. And this is if the other term wasn't there, you can see that this has a, right, so this is just a free boson, there's a free field theory, and then you add a perturbing term. So these are the perturbing terms that are compatible with sort of the spatial symmetries that you expect from this diamond model. Right, so now to understand the physics of this, right, so let's discuss two parameters in this Luttinger liquid. So one is this parameter K in the first term. This is the Luttinger liquid parameter. And then in the dimer model, K is equal to 1. This is also called the free fermion point. Okay. And then there's this other parameter, these BPs. So these are the potentials or the perturbing terms that you can add. And yeah, so this is basically the strength of the perturbation. It is sort of related to the lambda later on in the talk. Right. So why are we going through all of this? Well, we're going through all of this because we want to understand emergence in this framework. And emergence of the U1 symmetry in this case means the following. So if all the VP are equal to 0, then the theory has a U1 symmetry. And if you add any of the VP perturbations, then you break the U1 to a Zn, where n is basically P, or P over 4 if you want. So then you can, so this field theory is a field theory that has a U1. It's critical at the U1 point, and then when you break the U1, it can tell you whether you can open up a gap or whether the U1 symmetry remains emergent. And in this case, it's a conformal field theory. You can solve everything exactly, and you can figure out the scaling dimension of this operator, for example, that breaks U1 to Z2, which is precisely the thing that we have basically at the edge of our transfer matrix. And it turns out the scaling dimension of this operator is 2 over K. So at the dimer point, the scaling dimension is 2, and it's a relevant operator. And we know that the physics of the state should be gapped immediately away from the lambda equal to 0 point. Okay, so at this point, this has nothing to do with any RVB physics. So where's the connection? So the connection comes in this and other papers where you can extrapolate this dimer model to the RVB state. And the way that this works is basically you can go to a loop picture where this the interpretation of this Luttinger parameter is sort of the length of the loops that you keep in your system. So basically, dimers are SU infinity singlets, and then you go down to SU2. And the effect of this is that it renormalizes K. So this parameter K that you can see here in front of the free grad phi term gets renormalized from K equal to 1 to about K equals 0.6. Okay, so maybe one hypothesis for why we have this emergent symmetry is that at the RVB point, which is this Luttinger liquid at parameter K equals 0.6, maybe there's that 2 breaking perturbation is an irrelevant perturbation. Even though we break it on the level of the tensor, it comes back in the low wavelength limit. So you can convince yourself, and you do an easy calculation. You divide 2 by 0.6, there's the formula here, and you figure out the scaling dimension of this operator at the RVB point is 3.3. So it's less than 4, and 4 is the marginality condition. So if it had a scaling dimension greater than 4, it would indeed be irrelevant based on this field theory argument, but it's not. So then we conclude, even from this field theoretic argument, that the U1 to Z2 breaking on the level of the tensor should open up a gap, but it doesn't. So then you go back to this original paper that I showed, where they put forward this phase diagram, this extended critical region phase diagram, and now you look at how you come to this conclusion. Basically, this conclusion was drawn just from looking at correlation lengths, and there might be an alternative that explains this large correlation length in this lambda 0 to 1 region, which is that it's just simply not converged. There is a finite but very large correlation length. So maybe this is what happened. Okay, so in order to test that, we need to, so this regime lambda 0 to 1 is numerically extremely challenging. So we tried various different contraction schemes, corner transfer matrix and BOMs, and it turns out that getting these correlation length convergence is extremely hard. So we developed a new method that we call the correlator method. And the basic assumption of this correlator method is that is on this transfer matrix of this PEPs. So we assume that the transfer matrix sort of is is exponential of some Hamiltonian plus a perturbation, where this Hamiltonian corresponds to this blue unperturbed critical tensor in the beginning, and the lambda times sum of Vj is the red tensor that introduces local perturbations. So if you introduce the transfer matrix takes that shape, then you can compute the following quantity, which is you just write down your critical lambda equals 0 wave function and you compute this correlator, C of D. Now, because it's critical, typically this correlator will decay as d to some power, so it will decay algebraically. And this exponent of alpha you can extract, and this is relatively easy to do at the RVD point, even though it's hard to converge for the correlation length, even around the RVD point. So if this assumption is correct, then we predict that the opening and scaling of the gap, so the delta is this gap, so the gap or the inverse correlation length of this wave function, that is the critical tensor plus lambda, the perturbation, is scales like lambda to this exponent 4 divided by 4 minus alpha. And there's 3 cases, basically. So if the C of D decays exponentially, for example, this would be the observable that correlates to the spin-spin correlations in the RVD model, then it's an irrelevant perturbation and this doesn't open up a gap at all. Then if alpha is greater than 4, this is an irrelevant perturbation and there should be no gap opening either. And if alpha is less than 4, then there should be a gap, and you can and you predict based on this method that the gap should open in this fashion with this exponent. And in our case, if we compute this, you get exactly this 3.3, exactly the exponent you expect from a U1 to Z2 breaking at this particular point in the Lagrange liquid. So you expect a particular scaling. So you plug the 3.3 into this exponent and you expect some scaling. Okay, but before going to the RVD point, let's go to some easier models to check whether this assumption is actually valid. So you can do a few toy models. So you can dope the RVB, the nearest neighbor RVB, with holes. So this is a U1 to Z to nothing breaking. So it completely breaks the symmetry. And so indeed, there you can show that the exponent agrees relatively well with what you predict from the correlator method. So the blue dots are the correlation method extracted from the gap of the boundary transfer matrix. And the orange lines are the scaling extracted from this correlator method. And in this model, they agree very well, except in the region where you can't really converge or where the correlation length is too large, and in the region where the state is far away from a critical point anyway. On the other hand, you can look at something called the dimer solidomer model, which is a exactly solvable model where you basically break the U1 to Z2 in terms of the dimers. So you have sort of dimers and objects with 3 rods. And there this works very well as well. And now we go to the nearest neighbor RVD model, and it kind of doesn't really work. So you can see that there's this linear region that agrees fine with the prediction, but there's also this other stuff around. In particular, for small lambda, there seems to be a very pronounced bend that we can't really explain. So this is not really satisfactory. And the explanation for that comes from, well, let's recall the field theory of this RVD state. So I argued that at the RVD point, the field theory of the RVB, nearest neighbor RVB state, is basically all the VPs are equal to 0 and K is equal to 0.6. And now in this correlator method assumption, we've assumed that we have not changed the first term in the action, but only the second term in the action. So we only add a pure second term in the action. Now, instead, what could happen is that you change both at the same time. So on the level of the tensor, if you introduce this teleportation long-range singular tensor, maybe what you're introducing is some cosine terms that break U1 to Z2, but you might also renormalize K, in which case all the critical exponents float. And this is then called the sine Gordon model, which you fortunately can solve exactly. And in the regime where you can actually converge the PEPS correlation length, which is up to about 0.65, you find that both agree relatively well. So this is the data that we can get with good confidence are compatible with a perturbed Luttinger liquid where this perturbation is A, breaks U1 to Z2 and also renormalizes K. And then the conclusion that we draw is that the long-range family of the long-range RVB family that has been studied here is actually gapped with a huge correlation length. So even though U1 might be a good mechanism to give you a critical wave function, you can also get that type of physics even with breaking with an almost relevant perturbation, because the correlation lengths are really on the order of like several thousands and hundreds of thousands, something like that. That's the prediction from the correlator method for very small lambda. Okay, good. So okay, so that was a riot. So we thought that there's some emergent U1 symmetry, and we were very excited because this can't happen for finite groups. And now it turns out that's not the case. There's another much more mundane reason for why there's this large correlation length. So going back to the original question, can U1 symmetry, U1 virtual symmetry, and the associated criticality, can that be emergent in a PEPS? So now that we learned all these things, it should be relatively easy to write down such a PEPS, which is we take something that is described by the same field theory. So forget about the VP, and we just tune this K to be so small that for example, the U1 to Z2 breaking operator is irrelevant. So we just have to tune K smaller to a half. So this is, maybe some of you are familiar with how that works in the XXZ chain. So that basically is tuning the delta beyond the Heisenberg point. Okay, and then a PEPS, you can easily write that down in a 6-vertex PEPS. Okay, so a 6-vertex PEPS within an external field, there are points where K is smaller than 0.5, and indeed numerically we see that correlators that are related by this U1 symmetry, by this virtual U1 symmetry, after breaking the symmetry, there shouldn't be any relation anymore, but it turns out they still decay with the same exponent for all the distances that we can measure. So there's of course no proof, but it seems like these emergent symmetries are indeed possible, just not in the way that we thought originally. But this could be a first test bed to figure out a more general theory. Okay, so that brings me to the conclusions. So one, virtual symmetries have been studied for finite groups, and we're extending this to continuous groups, and the virtual U1 symmetry corresponds to symmetry breaking topological or gapless, so there has to be a second low-lying excited state, very similar to the original Lipschitz-Mattes Ishikawa theorem. In case this predicts gapless excitations, we can explicitly create them using these virtual photons. We come up with this correlator method for this niche application of predicting scaling of gaps and opening of gaps at critical points in PEPS. We figure out based on this that the long-range resonating valence bond family is actually gapped for any lambda equal greater than 0. So there's no emergent U1 symmetry for this particular family, but we put forward another system where we claim that there is indeed an emergent U1 symmetry. Okay, and this is all I have to say. Thank you very much. Again, shameless plug, we are hiring tensor network experts. I'd like to thank you for your attention, and happy to take any questions.
Thank you very much. So now this talk is open for the question. Do you have any questions or comment? So I have one question. So, do you have any comment about the phase diagram of square lattice J1, J2 model? So some studies suggest the gapless U1 spin liquid state in that model, I guess. So is it possible?
Right. So no. So the short answer is no. I mean, if I had to relate that to what I said, is then so the state that is the most competitive out of this family is right. So it is a state with a very large correlation length, but it's a gapped state. So it's a Z2 liquid with a huge correlation length. Now, of course, this is just the best state in this family, right? So it could still be gapless, or it could still be something completely different for all we know, right? Because this is the constraint that we have here. But according to this, if this was perfect, then it would be a gapped Z2 spin liquid with a huge correlation like that.
I see. Thank you.
With an almost irrelevant perturbation, sort of, where Z2 is almost irrelevant sometimes. Yeah.
Okay, thank you. So any other question? Please, Inje.
So can you measure other like excitations other than photons? Because do you know the dispersion of your spinons, for example?
Right. So yes. So you mean like make different excitations like explicitly, like write them down as a PEPs? That's a good question. So right. Right. So in the art, right. So measuring the observables, people have done this in this particular family of states. I mean, that's just a matter of defining things appropriately, like the spin spin-correlator in the RVB. That's relatively easy. Now, in a general way, so these theorems that I wrote down, they are for U1 virtual symmetry without an extra SU2, right? You might have systems that don't have an SU2, and then it's not so clear what the spin-on means in this case. So the fact that it's the RVB has this extra SU2 is kind of accidental here. But the interplay between the sort of virtual U1 that's going on and the spin-ons is there seems to be something interesting going on because of this loop picture. So they both have both the spin-on and these photons both have a loop interpretation. So they seem to be related. And also, if you tune from this SU, if you tune this SUN, you tune the N, then they both sort of get a different. They're both affected. So there definitely is a relation, but we haven't looked into this at all. No.
Okay. Yeah. Because I remember this Ingtang's paper. They used the variational Monte Carlo to look at how spin-ons. I mean, when you break up a bound, there's a spin-on interaction, and you kind of can see the how the excitations evolve. Yeah, but it'll be interesting to do this also in the PEPs.
Right. So you mean like actually the time?
Yeah, or you just get the excitation, see what kind of say spin-on excitation is like.
Was that dispersion or something like that?
Yeah.
Yeah. Yeah, that would be interesting. I agree.
Okay, thank you.
Yeah. Thanks.
Okay, so any other questions or comments? We have 7 minutes more. Okay, I have one another question. So today you consider the U1 symmetry. So is it possible to consider the other continuous infinite?
Yeah. So so we also looked at SU2, and it turns out that SU2 it's never critical. It's always symmetry breaking. And that is related to something called these quantum conformal critical points that Pendley and co-workers studied in like I think 10 years ago or something like that, where they tried very hard basically to find a critical SU with virtual SU2 in their language, and they didn't succeed. And they had some field theory arguments that were very complicated and out of my understanding. But essentially, whenever you try to, so the models that we wrote down, so you just write down 1 dimension 2, and you write down 1 dimension 3, and you look at the different things that are possible. It turns out you always get sort of loop models. So SU2 very naturally leads to loop models. And typically what happens is they break the rotation symmetry. So there's sort of packets. So they break the, well, rather they break the translation symmetry of like one shift over. So you have like loops here. There's like one ground state and the cat state between loops here and loops here. That's sort of the phase, and then plus some other stuff. So it seems that is just a symmetry breaking. I mean, it fulfills the Liebschutzmatis theorem in some sense, because because there's another state, but it's just a symmetry breaking state. So it seems like there's some so if you write down these photons, basically there's if you make this ansatz, it turns out it's not a well-defined state. Basically, you just the norm blows up and it's not well defined. So it's symmetry breaking. Yeah.
Okay.
Yeah. Thank you.
Thank you. So Wei-Ling, please.
Okay, thank you. So probably a naive question. So since your answers is well constructed, I wonder if it's possible to find out its model Hamiltonian.
You like the parent Hamiltonian?
Parent Hamiltonian. Yes, exactly.
Yeah, right. So for the REB in particular,
or the answers with a U1 symmetry that you are presenting
right.
for the perturbation.
I see. So that depends. So if you have, that depends on the bond dimension, because the larger the bond dimension, the larger you have to make the patch. I now that you said, that could be an interesting question. We haven't looked into it, because you could just say, take bond dimension 2. What are all the parent Hamiltonians? What is like the unifying feature of all of them or something, right? Do they have some funny symmetry that we don't know of? And this is something that we haven't looked at actually. So yes, it is. So finding explicit representation of these parent Hamiltonians is rather challenging, in the sense
I also
that
think so.
yeah, because like for the REB, like the smallest you can make is like 12 spin Hamiltonian. So these theorems, they work mostly by being locally indistinguishable. So they're like they're basically with respect to any Hamiltonian, because they're almost locally indistinguishable. So they have to have the same energy. So that's a bit easier than working with the explicit Hamiltonian. But no, I don't know. I don't know the characteristic of a Hamiltonian that would have that as the ground state. That's a good question. Thank you for the question. Yeah, I'll keep you posted.
Sure, that'll be great. Okay, thank you.
Yeah, thank you.
Okay. So any other questions or comment? If not, let's thank the speaker again. Thank you very much.
Thank you.